Karczewski, and with my fellow Igor Chorazewicz, we would speak about Pmemkv. So we are going to talk about Pmkv database, its purpose, and its design overview. Next, we go to overview of C++ API and how it's exposed to high-level languages. Then we go to the details of the internals of some of our storage engines and show some insight into problems we encountered during implementation. At the end, we would talk about our plans for near future. Pmkv is persistent memory optimized key value store. You may wonder why we need yet another in-memory key value store. So the barrier to adoption of persistent memory is bigger as we go into low-level aspects of persistency. So there is need for the part of the software stack which utilize persistent, yet it's easy to understand and maybe good starting point for the adoption of persistent memory-related concepts. We wanted to create simple key value store API which may be used in C++ and high-level programming languages and take the advantage of direct memory accessibility and huge size in comparison to DRAM. The API is designed to be similar to other well-known key value stores like the RocksDB and the LevelDB. The main difference between the Pmkv and databases backed by SSDs is that in Pmkv, we may efficiently operate directly on the data stored on PMEM instead of copying it from storage device into memory before doing any process. That's how Pmkv ecosystem is implemented. It consists of three main components. Core of the library, which is written in C++ and exposes API in C and C++. On top of C and C++ API, we may be implemented user application or high-level language binding. Currently, there are bindings for Java, Python, NodeJS, and Ruby. Under the hood, Pmkv uses different storage engines. Such engines differ in capabilities and purposes and are implemented using different libraries like PMDK for persistent ones, TBP and Memkind for volatile. There are also engines implemented entirely in the Pmkv codebase. We basically use three properties to categorize our engines: the ordered and unordered one, the persistent or volatile, and concurrent and single-threaded. So the user may choose the engine which is optimized for his use case. As engines are internally different data structures, it's not possible to open database created for an engine with another one without conversion. The API is similar to other well-known key value storages, as is inspired to RocksDB and LevelDB. So between open and close calls, we may put, read, remove, iterate over all data. For ordered engines, we may also iterate over some ranges accordingly to the specified key. Lately, for the better data flow control, we added iterators, API, and transactions. So let's look at some code example. At first, we need to create a config object, which is set in which we set parameters needed by engine we want to use. So we set path to the pool, which in our case is file placed on the file system created on persistent memory. Specify the size of the database and mark we want to create database if pool do not already contain the one created in previous runs of application. Then we create database object and call open with engine name and previously created config. After that, we may start reading, writing, and removing data. The whole point is to access data directly on the persistent memory without copying in anywhere. So we may get such access inside lambda expression passed into get method, like here. If the standard get API is not flexible enough for user's use case, we implement that iterator's API. Currently, it's experimental and may be changed in the near future. The main feature it provides is possibility to change part of stored value for the right iterator instead of overriding the whole value. This feature comes with additional constraints. User may only hold one iterator for each thread at a time, and it holds log on the accessed element, which may cause significant performance impact on multi-threaded applications. Another experimental feature we introduced lately is Transactions API. It allows grouping operations on the database, like put, get, and remove, and commit it or discard it atomically. After TX begin, we may, for example, put or remove some data, which will be visible after commit, or change it, or changes will be discarded on abort. Currently, it's not possible to use iterators and transactions in the same time. We also provide high-level languages bindings. 3 of it has already stable releases: Java, Python, and NodeJS. Ruby binding is in its very early stage. Every binding is made with a little bit different purpose in mind. Java binding is intended to leverage PMEM for enterprise application and provides flexible API to serialize objects before being stored. Python bindings is intended mostly for development of database management tools and database migrations, as it's possible to create database in Python and use it later in C++ application. Node.js binding is for backends of web applications. Bindings API are conceptually similar to each other. However, they have syntactic tweaks to be as idiomatic as possible for particular language. As you can see in Java, on the right, we create database objects using the builder pattern. On the other hand, in Python, we create simple config dictionary, which we pass to the database constructor. Here and here, we may see how to pass lambda expressions from the Python and Java to our get methods. We also provide Pmkv bench, which is benchmarking tool inspired by dbbench, which helps us to measure and optimize performance of engines. It may be very helpful for people who want to contribute engines. Okay, thank you. That's all for the first part.
Okay, thanks, Pawel. I will now take over and talk a little bit about Pmkv Internals. My name is Igor Chorazewicz, and I'm a software engineer at Intel, leading the team responsible for Pmkv and libpmob development. I will give a brief overview of our engines and share some lessons we learned while working on them. At the end, I will also share our plans for the near future. Most of the engines in Pmkv are based on libpmob. This library provides a transactional object store for PMEM and also offers several persistent memory optimized data structures. A lot of the engines are using those data structures underneath. Some of them are listed on this slide. You can see vector, string, array, segment vector, radix tree, which is actually stdmap compatible container, and also concurrent map and concurrent hash map. I will start overview of Pmkv engines with the CS map. It is based on a concurrent skip list implementation from libpmob. As you can see on the slide, the data structure is a multi-layer list. At the bottom of the list is an ordinary ordered linked list. Each higher layer acts as an express line for the list below. Number of layers is random for each element, and having only a single layer has the highest probability. CSMAP implements a weight-free search and uses per-element logs to synchronize insert and updates. On this slide, you can see complexity of different operations on this skip list. Right now, the delete operation for CSMAP is blocking. No other operation can happen concurrently with delete. This is because we use a weight-free, log-free search, which means we would have to solve the memory reclamation problem. We cannot remove element which can be read from other threads, so we need some mechanism for delaying the free operation. There are several solutions that we are evaluating right now, mainly hazard pointers and epoch-based reclamation, but I will talk a little bit more about that at the end. When speaking about CSMAP, I would also like to say a few words about Pmkv properties. I would like to focus on three things: atomicity of operations, read guarantees. For example, for current engines, we allow reading only committed data, so the data which is durably stored in persistent memory. And the third property, no persistent memory leaks. I believe that when developing a new data structure for persistent memory, it is very important to think about those three properties and specify the expected behavior. Once this is done, those properties must be implemented properly. From our experience, this is not an easy task. That's why we have a few tools which help us with that, mainly Pmemcheck and PM reorder. Right now, I would like to present a few common mistakes which violate the properties I mentioned. After that, I will show a framework which we use in Pmkv to guarantee consistency, atomicity, and avoid those memory leaks. I will use CSMAP as an example. As I mentioned before, CSMAP provides log-free search. This means that we have to use atomic instructions to avoid data races between readers and writers. Let's now take a look at how we might implement insert operation for CSMAP using libpmopch CPP. We might come up with a code similar to the one presented on this slide. We use libpmopch CPP transaction to allocate new node, and then within the same transaction, we insert the node to the list using atomic store. Unfortunately, this code is not correct. Because we insert the new node before the transaction ends, so before the allocation is actually treated as persistent, and when it's still subject to a rollback, other threads can see an uncommitted state. If a transaction rollback happens, when some other thread is reading from this new node, we have undefined behavior. And this also violates one of the properties I mentioned before. Okay, so maybe let's try a different approach. On this slide, you see that the atomic store is done outside of the transaction to avoid problems with reading uncommitted data from other threads. But now, if a failure would occur between transaction commit and atomic store, we have a memory. We would have no way of accessing the new node since the only reference to it was on stack. So this is the PTR variable on this slide. Here, you can see our solution to this problem. We use a data structure, which we called persistent TLS. You can find it in libpmopch CPP under the name of pmopch enumerable thread specific. You can find it under the link on this slide. And it offers per thread storage on persistent memory. We use this structure to hold pointers to all nodes which are not yet inserted to the list, so they are not yet globally visible. Since the storage is per thread, we can safely use it inside of a transaction. Thanks to persistent TLS, each allocated node is always reachable in case of a crash. So after a crash happens, we can just iterate over all the nodes in persistent TLS and redo interrupted operations or just remove the nodes, depending on what guarantees we want to provide to the user. On the bottom of this slide, on the image, you can see that insert consists of two steps. First, we allocate the new node and insert it to the persistent TLS in a single atomic transaction. And only after this is completed, we insert the node to the list. This slide presented the approach which I just described in code. As I said, allocation and inserting to persistent TLS is done in a single atomic step in a libpmop CVP transaction. After the transaction ends, after the data is safely committed, we just use normal atomic store outside of the transaction to insert the node to the list. We still have to guarantee that the store reaches persistent memory, so we use persist after this store. Okay, let's now move to another engine, to CMAP. This engine is based on Pmemkv concurrent hashmap, which is inspired by it is based on Pmemkv concurrent hashmap, which is based on TBB concurrent hashmap, and it uses separate chaining as a conflict resolution mechanism. CMAP uses optimistic per bucket read-write lock, and each operation in CMAP the following actions. First, it finds required bucket using hash of the provided key. Then it locks the bucket for read or write access, depending on the operation. And this ensures that only a single thread can modify the bucket elements. Once the access to the bucket is obtained, it scans all the nodes in the bucket to find a matching entry. Each node in the bucket also is protected by a read-write lock. You can find more detailed description of CMAP and CSMAP in one of my previous presentations, concurrency in failure atomic data structures. A link is provided at the end of the presentation. You can also look at the implementation, which is present in libpmop CPP. And similar as for CSMAP, on this slide, you can also see the space and time guarantees for this data structure. On this slide, you can see layout of a CMAP node. It consists of a next pointer to another node in the bucket, a mutex, actually read-write lock, and an item, key value pair. It turns out that this is not the best design. The fact that we have mutex on persistent memory affects performance. Each lock and unlock operation might write to PMEM. Even though we do not explicitly flash cache lines, those cache lines might be invalidated when accessed from different cores. Since PMEM is slower than DRAM, this is very problematic. We have this problem in CMAP, CSMAP, and VCMAP engines. VCMAP is a volatile version of concurrent hashmap, which uses PMEM. A natural solution would be to move locks to DRAM. In general, we see two options which are feasible for Pmkv. One is to avoid using per element locks and just use sharding instead. We can partition the database into multiple single-threaded containers, each protected by a read-write lock. This usually works well in practice, but only for unsorted engines. I will show an example of such engine in a few slides. One other approach we might take is to only keep lock in DRAM, but have a pointer to this lock on persistent memory. So this is feasible for large elements, and it is possible to implement with our existing containers. So for example, Pmemkv concurrent hashmap, but also with TBB concurrent hashmap, if you would like to use that in a volatile mode. On this slide, you can see how you can achieve that for TBB. This change was recently added to the TBB, although it is not yet released. Okay, now let's move to another engine, Radix tree. In our implementation, there are two types of nodes, internal and leaves. Leaves contain key value pairs, and internal contain array of pointers to children. It is very similar to a B plus tree. Each edge between nodes has a label consisting of one or more bits of the key. Finding an element can be done by comparing labels with bytes of the key we are looking for. You can see an example Radix tree on this image. In terms of capabilities, Radix tree engine is persistent, single-threaded, and sorted engine. Radix tree is a very good fit for PMEM because it does not require any rebalancing, so number of writes is minimized. And since we do not rely on key comparisons, like in binary tree or B tree, number of reads from PMEM is also minimized. When implementing Radix tree, we did one important optimization. In most other data structures, for example, CMAP and CSMAP, we store keys and values as strings, specifically as PMEM strings. This results in additional allocations which are costly on PMEM. You can see this on this slide. With PMEM string, the data must be allocated separately from the node in the Radix tree. However, we came up with an idea of inline string, which we use right now in Radix tree. This is a data structure which holds data in the same allocation. On this slide, you can see that when using inline string, both metadata, value, and key is stored within the same allocation, which improves performance. Of course, this solution has some drawbacks. Most notably, if we want to update the element and new value is bigger, we need to reallocate the whole node. However, it still works well in practice. I will end this part with a brief description of Robinhood engine, which we have recently added. It is a persistent, concurrent, and unsorted engine. Currently, it supports only 8-byte keys and values, but offers much better performance than other engines. It uses Robinhood hashing, which is a variant of open addressing, and it's very cache-friendly. This engine uses sharding to achieve concurrency. So there are basically multiple shards protected by a read-write locks in DRAM, and each shard is just a single-threaded hashmap implementation which resides on PMEM. Last technical thing I wanted to mention is a performance problem which we had with Pmemkv person pointer. Our data structures make extensive use of person pointers, specifically Pmemkv person pointer from the Pmemkv CPP. On this slide, you have a pseudocode which shows how a person pointer is implemented. It is a 16-byte fat pointer which stores pool ID and offset within the pool. Some time ago, we encountered a performance problem related to the usage of this pointer. In some cases, it was over 100 times slower than a normal voltage pointer. After some investigation, we found out that the problem was in Pmemkv direct implementation. And Pmemkv direct is a function which is called on each pointer the reference. You can see this function on this slide. The function used a thread local storage to cache pool's virtual address offset, which prevented many compiler optimizations, including vectorization. This was the main problem from the performance perspective. Our solution to this problem is a new type of pointer, self-relative pointer. It is only 8-byte and has the same performance as normal voltage pointers. You can see the main idea on this slide. So instead of storing absolute offset, it stores offset which is relative to the pointer's location itself. On the reference, we just sum up the address of the pointer and the offset it stores. Of course, this design makes it impossible to have cross-pool references, but we found that most pointers are used only within a single pool. Self-relative pointer also provides STD atomic specialization, which makes it very easy to use this in a log-free data structures. For example, we use self-relative pointer in a CSMAP implementation, and we will also use that in Radix tree. Okay, that's all I have prepared about Pmkv internals. Now, a few words about our plans for the future. Right now, we are working on a heterogeneous engine. So this will be a new engine which would use both PMEM and DRAM to increase performance. We want to implement it as an extension of Radix tree. You can see a general idea on this slide. So there is a persistent lock which acts as a write-ahead lock, and each new put to this engine only appends the data to the PMEM lock. This should be very fast operation. And apart from updating the lock, it also updates the DRAM index. Data from lock is moved to the Radix tree in a background thread. You can expect a more detailed explanation of this engine on our blog post pretty soon. Apart from that, we are working also on solving the problem of memory reclamation. It will allow a single writer multiple readers to execute concurrently for some of our existing data structures, mainly Radix tree, and it will also help to make the csmap delete operation concurrent. We also plan to extend existing bindings functionality. So our main focus right now is on Pmkv Java, optimize existing engines, and publish regular performance reports. Right now, we gather performance data from Pmkv Bench, which was already mentioned by Pawel. Pmkv Bench is based on LevelDB Bench tool. But now we want to extend the benchmarking capabilities and upstream a Pmkv client implementation for YCSB. In near future, you can also expect more educational materials about data structure design on our pm.io page. If you want to learn more, check out the links or reach out to us directly. I especially encourage you to take a look at our PM book, which covers many topics, including persistent memory data structures. That's all from me. Thank you very much for listening.